And now, coming to you live from the great halls of Tarakas, AB Calculus. Dance. 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 Section 2.1, Rates of Change and Limits. A few weeks ago, I went out to Lynn Canyon with my family, and my oldest son loves throwing rocks into the water. So when we got up to the pipe bridge, we threw rocks from there down to the river below. As the rocks fell, we counted to see how long it took until they hit the water below, and we usually counted up to about 4. See, a rock that's dropped from the bridge will fall a distance of 16 t squared feet over a period of t seconds. So if we calculate the distance that the rock has fallen, we've got distance is equal to 16t squared, or in other words 16 times 4 squared, for a total distance of 256 feet. So what would be the speed of the rock? Well, we all remember grade 9, speed is total distance over total time. So we go 256 over 4, and we get 64 feet per second, which is pretty fast. But I'm not sure that this is right. I mean, we know that objects that are falling toward the ground will be accelerating due to gravity until they've reached some terminal velocity. And I'm not convinced that the rock has reached this speed yet. Let's consider a table of values for the distance and the velocity of the rock over the first 4 seconds. We can see in the table here the distance traveled after each of the first 5 seconds and the corresponding speed calculation in feet per second. And we can see that the velocities are increasing here, but even so, if we could somehow put a speedometer on the rocks, we could see that their instantaneous speed is much faster. These are just the total distance over the total time. There's the average. So why don't we calculate the average speed between 2 closer points? For instance, what if we did the average speed from 3 to 4 seconds? In this case now, we're getting 112 feet per second, which I think is closer to the actual speed, but it's still just average over that 1 second interval. So let's try one more time, but now by finding the speed between times t equals 4 and t equals 4 plus h, where h is a very small value. So I'll start off by calculating 16 times 4 plus h squared minus 16 times 4 squared all over 4 plus h minus 4. So I've got difference in distance on the top and difference in time on the bottom, or delta d and delta t. And expanding these statements and calculating them, the bottom simplifies down to h, and on the top we finally end up with 256 plus 128h plus 16h squared minus 256. Obviously the 256's just cancel each other out, and we've got a common factor between these 3 terms of h, and when I remove that common factor of h, this simplifies down to 128 plus 16h feet per second. And I think in this case it's easy to see that as we make h sufficiently small, that the speed will simply be 128 feet per second. And that, my friends, that's what we call a limit. Definition. The limit of a function f of x is written as limit of f of x equals L as x approaches a, which means that the value of the function is very close to some real number L as x gets sufficiently close to, but not equal to, some real number a. So you could have x approaching a either from above or below a, and the value of f of x gets closer to L as x gets closer to a. So in the case of the falling rocks, we could say that the speed of the rocks at t equals 4 is given as the limit of 128 plus 16h as h approaches 0. And this obviously is equal to 128. Let's try a new example then. Give the value, or find the value, of the limit as x approaches 1 of x minus 1 over x squared minus 1. Well, obviously in this case we actually cannot allow x to equal 1 because it would make the denominator 0. So there are 2 approaches that we could take here. We could just look at a table of values centered at 1 and see what happens as x approaches 1 by small increments, and we will see the limit of this function appears to be 0.5. Consider the following three functions, f of x, g of x, and h of x. And for all three, if we think about the limit of the function as x approaches 1, of course they actually do different things at the value of 1. H of x at 1, we have the point 1, 2. That's fine. But on f of x, the point actually does not exist, and of g of x, 1, 2 doesn't exist, but because it's a piecewise function, we've generated the point 1, negative 1 on here. However, in all three cases, the limit of the functions as x is approaching 1 is 2. So we've defined the concept of a limit. I want to explore just a few properties of limits before we go on and do some more calculations and evaluations of limits. So just a few things here briefly. First of all, some definitions. L, M, C, and K are all elements of the set of real numbers, and the limit of f of x as x approaches c is L. The limit of g of x as x approaches c is M. Given these statements here, then the following properties about limits are true. First of all, we have the sum rule. The limit of f of x plus g of x as x is approaching c is equal to the sum of the two individual limits, the limit of f of x plus the limit of g of x, in which case we get the answer L plus M. Likewise, we have a difference rule. The limit for f of x minus g of x as x approaches c is simply the limit of f of x minus the limit of g of x, or L minus M. Next, we have our product rule. The limit of f of x times g of x as x approaches c is simply the limit of f of x times the limit of g of x, in other words, L times M. Next up is not, in fact, the quotient rule, but the constant multiple rule. And we're going to scroll down here so we can see that better. The limit of k, some constant, times f of x as x approaches c. Well, k is unaffected by what x is equal to, so we can bring k out front and say this is simply k times the limit of f of x as x approaches c. We already know that limit is defined as L, so the value is k times L. Next, we have the quotient rule. The limit of f of x over g of x as x approaches c is simply the limit of f of x over the limit of g of x, which is L over M, provided, of course, that M does not equal 0. And finally, we have the power rule. If we also allow r and s to be elements of the set of integers where s can be any non-zero integer, then we have the limit of f of x to the power of r over s is simply L to the power of r over s. And you can see why s can't equal 0 in this example. We can evaluate polynomial and rational functions by substitution. A function is considered a polynomial function, f of x, if it is of the form f of x equals a sub n x to the power of n, a sub n minus 1, x to the n minus 1, and so on, where a is an element of the real numbers, all the a subs are real numbers, and the n's are all natural numbers. In the case where c is an element of the real numbers, then the limit of f of x, our polynomial function, as x approaches c, is simply equal to f of c. And since a rational function is defined as f of x equal to g of x over h of x, where f and g are both polynomial functions, we can also say that the limit of f of x is equal to the limit of g of x over h of x, which of course follows our quotient rule from before, giving us simply g of c over h of c as the limit for f of x, provided, of course, that h of c does not equal 0. So, to evaluate the limit of x squared minus 6x plus 9 over x plus 3 as x is approaching 2 gives us simply 2 squared minus 6 times 2 plus 9 over 2 plus 3. This is equal to 4 minus 12 plus 9 all over 5, and so we get is 1 over 5. Let's take the example we saw earlier. We already know this is equal to 1 over 2, but we can't substitute 1 in here because it's going to cause the denominator to equal 0. But we can work to simplify and reduce this function before even doing the substitution. For instance, we know that x minus 1 over x squared minus 1 is the same as x minus 1 over x plus 1, x minus 1. And of course, we've got a common factor of x plus 1 in the top and the bottom, which can cancel out, leaving us with 1 over x plus 1. So why don't we instead find the limit to this function as x is approaching 1? The limit as x approaches 1 of 1 over x plus 1 is simply equal to 1 over 1 plus 1, or 1 over 2. We need to explore the concepts of one-sided and two-sided limits. When a function tends towards different limits as x approaches c from opposite sides, then we call the limit of f of x as x approaches c from the right. Notice a little plus sign there. We call this the right-hand limit, where x approaches c from above, from greater values. That's why we have the plus there. And likewise, the limit of f of x as x approaches c from the left, from below, we put the negative sign there. This is called the left-hand limit. So in order to say that the limit f of x as x approaches c actually exists, it must be true that the left-hand limit and the right-hand limit are equal to each other. In class, we'll take a look at something called the greatest integer function and explore this concept of one-sided and two-sided limits a little bit more with that. So please ask about that if I forget to do so. We've got one last thing to talk about here, and it's probably the most delicious concept yet: the Sandwich Theorem. The Sandwich Theorem says that if g of x is less than or equal to f of x, which in turn is less than or equal to h of x, for all x not equal to c, but in some interval around c, and if the limit of g of x as x approaches c, and the limit of h of x as x approaches c, if both of those limits are equal to L, then the limit of f of x must also equal L. In other words, if the function below f and the function above f both have a limit of L, then f of x must also have a limit of L. Now, I will agree that at first this seems to be a bit of tomfoolery and trivial silliness here, but it's one of these theorems that we'll encounter in calculus this year, which can harness its simplicity to produce powerful results. For instance, evaluate the limit of x squared times sine of 1 over x as x approaches 0. Well, we can't do a substitution here because 1 over 0 is undefined, so we can't even take the sine of that value. On the graph, it appears that the limit is 0, and as I said, substitution is impossible here. Let's zoom in. It looks like it's 0, but it also looks like it's doing some crazy stuff in there as x is getting closer and closer to 0. So I'd like to be able to have something a little bit more substantive than simply pointing to this picture and going, I think it's 0. So let's consider what we know about x squared times sine of 1 over x. We know the values of sine theta always go between -1 and 1. So the function y equals negative x squared must always be less than or equal to our given function. And likewise, y equal to x squared must be greater than or equal to our function. So let's consider the limits of these upper and lower functions, the ones which sandwich our given function. We can see clearly that the limit of negative x squared as x approaches 0 will be 0, and the limit of x squared as x approaches 0 is equal to 0. And therefore, the limit of x squared times the sine of 1 over x is also equal to 0. Alright guys, I know you don't want this to end, but it's time for me to go. But before I do, everybody's favorite part, that's right, 2 for you! Determine the following limits by substitution, and then consider this piecewise function over here. Find the following limits and values, or if they don't exist, explain why they don't exist. If you got any questions on this stuff, make sure you ask in class. But in the meantime, keep your pencils sharp, and I'll be seeing you in class.